Mechanical engineering, right now we go to the 2-degree freedom, that is chapter 5, and multiple degree freedom, chapter 6. And they both share the concept pretty much similar, so I decide to combine the two things together. And in our textbook, and they spend quite a bit of content in the equation of the motions, including Lagrange equations. To save our time, I will try to not to put not much time on that one, but I will show you how to do the equation motion in the right way. And there's a new concept in multiple degree freedoms, and that concept basically, okay, this is our the slides and the here, and here for this one is for your reference, and that exactly the sections I'm going over regarding our textbook. So for any particular readings you want to go forward, refer to those sections here. And the notes here, that should be have something available to you on Blackboard. So here I want to show you the first one, the first features of the multiple degree freedom that we cannot see in single degree freedoms. It's called the vibration mode. Okay, and we call the vibration mode, or we call the mode shapes, or sometimes called the modal vectors. Okay, and so here is the kind of schematic. We using the 2-degree freedoms. Here we have two mass, basically 2-degree freedoms, and this is one scenario of the vibrations. Basically, the two mass basically they vibrate in synchronized. Okay. The other possibility, the two basically they vibrate in opposite directions, okay, but at the same amount, right amount of the time. And this one basically showing is a combination of the two modes, okay. So here let's use the modes, okay. Basically the modes, you need to pick up the modes, basically it's a vibration mode. For example, for this case, the two objects moving in the same phase, that's the one mode. This one, basically, they're moving in the opposite, that's the second mode. Okay, and for the first mode, for this particular example, they can moving in the same phase, but they can move into this, they can move in a different magnitude. Okay, for example, this move 1, this can be 1 to 2, and this can be 1 to 2, okay, so that is the 1 to 2, something like this. And similar to this one, so although they can be in the same phase or out of the phase, opposite phase, but their vibration magnitude ratio could be different. Those kind of difference is determined by the mass of the mass block, and also determined by how strong the spring constant we use. So by all means, before I move on to the next page, now you need to pick up is the concept of the vibrational mode, vibration mode. Okay, so let me ask you, what is the vibration mode? Simply, that is a pattern of the relative motion of the two mass blocks. Okay. This is I tried, and this is the only one I kind of can find. So look at this one carefully. Okay, basically this is using the 3 mass blocks, and this one basically is this stick is to kind of give them the different initial conditions. Okay, so initially the 3 mass blocks, they basically sit in equilibrium, and then they use a stick to compress them or to stretch them. So that gives us the different initial conditions. Okay, so we see what happens. So here is a movie. And basically, each represent the vibration of one corresponding to one initial condition. So basically, here we're showing is to compile 3 different vibrations together for the sense systems. Okay. So they move. So this you can see. This one very clear. This is kind of stationary, and this one is moving in this way. So this is one mode. And let me see this again. For the second one, basically the three moving in the same phase, that's a one mode. And this is another mode. This is not, so we cannot see, identify explicitly, but we can calculate that one. Okay. And here, basically, this is one example, and this is the link. If you're interested, you can go to take a look at. And here is the three degrees of freedom, because here we have three mass blocks. So the number of the vibration modes equal to the number of the degree of freedoms. Okay. So here the very first and qualitative description is we talk about the degree of freedoms, and corresponding to the number of the degree of freedoms that has the same numbers of natural frequencies, they have the same numbers of the vibration modes. For example, 3 degree of freedom vibrations, you should expect 3 natural frequencies and 3 vibration modes. Okay, and the 2 are the first part we need to learn how to calculate, and that is the major contents of the homework 12. Okay, I designed. So the first one, let us focus on the equation of motions. So today, I will spend many time to quickly go over this one. So equation of motion, and here, if we are able to use Newton's second law smoothly, carefully, then we should be able to use that law to derive all the equation of motions. Okay, although textbook provide us the second approach called the Lagrange equations, I don't think I have time to go over that one for you. Okay, so I decided I put the focus here. And for this one, basically the way to apply Newton's law is to take a free body diagram on each of the mass block. Here we have 2 mass blocks, so here we have 2 free body diagrams. And so for this, let me draw this one. So this is exactly what we need, but here you can follow with me. So here, let me draw the free body diagram of the mass block here. Let me repeat the work. Okay. So assuming this mass block is moving in the direction of the degree of freedom. So under these situations, due to the movement of this mass block to here, this spring is stretched. So that will apply the force to bring it back. So that is the K1, X1. Okay? On the other side, I assume for my formulation purpose, okay, it will be easier. Here I give you a tip. It will be easier for you to imagine if mass M1 move to here, if mass M2 move to here. So here you can see what I'm drawing. This is X1 and this is X2. In my drawing, I assume X2 is greater than X1. You assume one scenario and stick with the scenario you assume. Everything will be consistent when you have the equation of motion formulated. Okay, and assume one good scenario for formulation. That'll be easier for you to. Okay, so here based upon my assumption, I assume X2 is greater than X1. In this way, this spring is stretched or compressed. Which one? Based upon my assumption. Because right now X2 is greater than S1. This point have a larger displacement than this one, so this spring has been stretched. If that has been stretched, then that means that will have a force dragging in that direction. How much? That is K2 and multiply X2 minus X1, right? So again, that is what I mean. Once you assume that and stick with your assumptions, this is the magnitude in the directions. Be okay? Okay. And so here is the M2 here. So again, this spring connect to each other. So this force, respect to this one, that simply is the alternate reaction. So that is the force. You simply copy the same magnitude, but reverse the force. and to copy that one from here to this free body diagram. Okay. Are we good? Okay. So once you have this one, then using Newton's law, this one basically equal to m1, and follow up the assigned directions and of the degree of freedom. So that is the x double dot. Okay. So this one again, this is m2 and x2 double dot. So from here you can formulate for this one, that means m1 x1 double dot, and in our sign convention positive here, so that basically equal to this force minus k1 x1 and this force plus k2 x2 minus x1. Okay, so this equation basically is this one. Good. So carefully apply carefully apply the free body diagram. For this one, basically that is m2 x2 double dot, and by Newton's law, and that is the force positive. So basically that is minus k2 and x2 minus x1. So this equation basically equal to this one. You good? So for this part, applying Newton's law, nothing special, but a little bit tricky is here, this how to deal with the spring that coupled the mass block. And that one, basically, if you like, again, and using my tips, you can always assume one degree of freedom is larger than the other one, and that'll be easier for you to graphically write down the right directions with the right amount. That be good? Okay. Okay, so with this one, then any questions about this? Okay, so with this one, you can see we have the 2 degree of freedom here because we have 2 mass blocks. So you should expect that the 2 equations of motions. Okay, so that's a little bit different from what we learned in single degree of freedom. We always have 1 equation of motion back there. But here, numbers of the equation of motion basically is determined by the number of the degree of freedom. The same thing that determines the number of the natural frequencies and the vibration points. Okay. Keep this in mind. I want to show you how to write. Once you have this one, then usually in multiple degree of freedoms, we like to express the equation of motion in a matrix form. So this is another new thing you need to pick up. The equations of motions in the matrix. Okay. So this one exercise basically is based upon this. Let me make one example, and before we apply this to this one. So if we have a x plus by equal to a1 c1 and a2 x plus b2y equal to c2. For example, if we consider this simple set of the linear equations, I want to, yes, question. Okay, I want to express this into a matrix form. The matrix form is such that I arrange here, we have 2 variables, x and y. So x and y are our variables here, okay? So I arrange our variables in vectors, the vectors of our variables, okay? So here is the notations I pick it up, and that along with our textbook, we use the kind of the angle bracket to indicate that in the vectors. and we're using this square, the bracket to indicate that is a matrix. Okay, just simply notation. So from here you can see if you have the matrix is such that if you remember A11, A12, A21, A22. For example, this is a 2 by 2 matrix, right? Very easy. And this is called the first row, and this is the second row. Okay, and this is the first column, and this is the second column. So let me use. So here you can see I simply use the colors to indicate the first symbol of the element in a matrix indicate is which row it is. So this is the first row and this is the second row. Okay. So when you describe the element, its index start with the number of the row, location of the row. The second index indicating which column you are in. Okay, so that is the notation for matrix. Okay. So for this one, if we want to multiply with xy, then simply from linear algebra, what we learning is this. This is called the algebra of the matrix. So simply you multiply this row with this column, that becomes A11x, corresponding element multiplied together, plus A12y. Okay? So this is the two elements multiplied corresponding to each one. Again, here is the definition or convention of the linear algebra with matrix and vectors. The same thing, the second one, this is this row multiplied with the 2, so A21x plus A22y. Okay, so here this is a 2 by 2 matrix, and this is a 2 by 1 matrix, or simply the vector. Vector is a spatial form of the matrix. So here, for anything we manipulate, then basically the two things will be out. The final form will be 2 by 1. So that is the expected format of the answers, 2 by 1. Okay. So for this case, if we reverse, if we are given this one, how can we write the matrix form? We look at this equation carefully. Right now we have laid out the vector here. This equation is simply equal to these numbers multiplied with x plus this number multiplied with y. That number is equal to a1. And this number equal to b1. And equal to c1 here. Right now I'm writing simply is a reverse process of practice here. Okay? A1 times x plus b1 times y equal to c1. Okay? Try to get used to. And the second equation that representing by the second row operations, a cubed multiplied with x, so that is a2, plus b cubed multiplied y, so equal to c cubed. Be good? You need to pick up this one, okay? And if you say, hey, I have a feeling, well, I feel not good, then try your best and go linear algebra. I think that's a keyword you can use to search for any textbook, any book from the library. Okay. So keep this in mind, then we can work on this. So right now we have two sets of equations. So basically here we can come up with this. So let me define x1 double dot, x2 double dot, and multiply with center something and plus something, multiply with x1, x2 equal to 0, 0. Okay, so basically here we have two sets of equations, and we do this one by one. Basically, right now I want to implement is what we get here. Okay, using apply this one to here. So the first term is n1 times x1 double dot. So that means n1 times x1 double dot. Okay, and then do we have the x anything multiplied with x2 double dot in the first equation? No, so 0. Okay. Then go to here, anything multiplied with x1, so that should be this term here. And that term is k1 plus k2. Okay? And then multiply with x2 is minus k2, so that is, I need to enlarge this one a little bit. That is minus k2, so that is another number. That's it. You good? Then we can look at the second equation. The second equation, the first term is m2 multiply x2. So tell me where is m2? Left or right? Right. So here is m2. And how about this number here? 0. Okay. So we deal with this one already. Then we look for this one. So that is something multiplied with x1. So this is a number multiplied with x1, that is minus k2. Okay, and then this one with multiplied with x2, this is here. Okay, so here let me get rid of this bottom line here. If you like, you can parentheses. So basically this is the 2 by 2 element. This is a 2 by 2 matrix. This is a 2 by 2 matrix. And usually in the people call this the mass matrix. There's a definition. This is called the stiffness matrix. Okay. And usually in our textbook we using these notations. So they are using this again, the square bracket to indicate that is a matrix, and simply use m, that is the symbols to indicate that is a mass matrix. So for 2 degree of freedom, this is the 2 by 2. For 3 degree of freedoms, the mass is 3 by 3, etc. Okay, and similar to k. And for the degree of freedoms acceleration, they use the top arrow to indicate that is a vector. Basically, this is a vector composing the degree of freedoms here. So, for example, here we simply define this one is degree of freedoms in a vector form. Okay, so basically this is a vector. This is the column vector. I'm right now talking is the very standard, the conventions for or format for describing the equations of a motion. Okay. One final thing is this. For your exercise, not only to write up the right equation of motion, you also need to force yourself to see whether you are able to write up this matrix forms expression very quickly, correctly. Okay, and if you have done this correctly, and if you put this form correctly, and I can provide you one quick way to check whether your work is right or not. If everything is right, the mass matrix and stiffened matrix, they must be always symmetric. If you would find your matrix is not symmetric, that's indicating something wrong in your process, and go back to check your derivations. Okay, be good? Okay, so coming back, yes.
So that symmetry requirement is just due to the nature of these equations that we're laying out?
This one come up with is the nature of the, I would say, most of the regular vibration systems. And I can guarantee this is the one for the system we're going to talk about in MB408. For other eccentric systems, they might not have, but it's not our discussions here. And
so, what does it mean by symmetric when you're...
Symmetric, oh, yeah. Sorry, that's my mistake. So, for example, 3, 1, 2, 2. Symmetric, that means if we use the diagonal, and then those numbers are the same. Let me use the 3 by 3. So, for example, 1, 2, 3. Okay, so here is -1, then -1, and -2, -2, and this is 4, this is 4. You can see I use the diagonal, and then the elements is the same. They simply symmetric is aij equal to aji. That is the definition for symmetric elements. Okay, so this element is, for example, this element. Let me say this element is has an index. This element has an index 1, 2. This element has an index 2, 1. Basically, follow up this kind of definition that is symmetric matrix. Okay, good. Okay, so I think Wednesday I will spend a bit more time to go over the different problems for equation motion.